It's my pleasure. That all good. It's my pleasure to introduce today's speaker, Dr. Sophie Coulson, who comes to us from the Los Alamos National Lab, where she is the director's postdoctoral fellow, which is quite prestigious. But before that, she completed a master's degree in geophysics at University of Liverpool, where I respect that highly because we've had to endure Liverpool for so long. After that, she then moved to actually during that, she did a year abroad at McGill in Montreal. So I guess was tempted to return to North America and did her PhD at Harvard University with Jerry Mitrovica. And that's where I met Sophie. And during her PhD and during her postdoc, she's worked on many problems. So she has publications in seismology, in geodynamics, in glacial isostatic adjustment, and sea and ice level, ice dynamics. And so today we're going to be learning about predicting and observing patterns in modern sea level forms and crustal deformation. So take it away, Sophie.
All right. Thank you for the thorough introduction, Harriet. Well, a little bit of Manchester Liverpool rivalry. Yeah, so today I'm going to be talking to you about a couple of different projects that I did as some as part of my PhD and some ongoing work as part of my postdoc at Alamos, as Harriet mentioned. So I'll jump straight into it. If I can have that slide. So when we consider global climate and changes in Earth's ice sheets and oceans, from a climate science perspective, we often assume that the Earth is rigid. But in reality, as you all know, we have deformation occurring within the Earth that can change topography and generate feedbacks with surface processes that have the potential to alter regional and global climate systems. And so my work really and this talk is designed to explore the feedbacks between those solid Earth dynamic processes and climate systems. So I wanted to begin with a bit of a thought experiment or a pop quiz for you all, and we'll kind of return to this theme, to this question as we move through the talk. So what would happen to sea level here in Berkeley if the Greenland ice sheet rapidly lost enough ice mass to raise global sea level by 1 meter? And I'm hoping to convince you throughout this talk that answering this question requires a full understanding of solid Earth dynamics. So when we consider deformation of the Earth, we have to consider the timescales on which different processes are acting. So the rheological response of the Earth depends on the timescale of pulsing, which is something that Harriet knows a lot about. So at the longest timescales of millions of years, on the left-hand side here, our Earth acts closest to a viscous fluid, so closest to our honey analogy. If we apply a stress to the material will begin to flow. Whereas at our fastest timescales, our kind of seismology timescales, seconds to decades, the Earth acts closest to an elastic material. So if we apply a forcing to the material and then remove it, it's going to return back to its original shape. And then we have these kind of middle timescales in here, intermediate timescales of centuries to tens of thousands of years, when the Earth acts closest to a viscoelastic material. So here my analogy is silly putty. If we apply a fast forcing, we hit our silly putty with a hammer, it acts in a brittle or elastic manner. Whereas if we leave the silly putty on the desk overnight, it's going to begin to spread out more like a viscous material. And so then to bring this back into the perspective of the Earth and how these different responses of the Earth over these different timescales affect our cryosphere, our ice sheets and climate. On the viscous side of things, we have on the millions-year timescale, we have upwellings and downwellings generated by mantle convection that can cause perturbations in surface topography. So if we have a warm upwelling in the mantle, that may exert a pressure on the surface and elevate surface topography, which in turn can change sea level and affect ice sheet stability. And then at these intermediate timescales, on hundreds to tens of thousands of years, the Earth is viscoelastically deforming in response to ice sheets moving around on its surface and our oceans moving around as those ice sheets melt. And then on the shortest time scale, in terms of ice sheet loading and ocean loading, we have almost elastic deformation driven by modern changes in our ice sheets. And so my work kind of focuses on understanding these processes on this whole variety of timescales and the feedbacks between these different ice sheet and ocean processes and our dynamic Earth. But today, what I wanted to focus on is these shorter timescale processes. So I'm going to focus mainly on modern changes in our ice sheets and ocean and the elastic deformation associated with that. And that'll include a little bit of viscoelastic Earth too, as our Earth adjusts to changes in ice loading over ice age cycles. But I've also worked more on these longer scale timescale processes too, and so I'm happy to chat about those at any point. Okay, so in order to first think about sea level problems, we need to understand a bit about the physics of sea level change on this elastic or viscoelastic Earth timescale. So when an ice sheet melts, there are several processes that are at play. There's kind of the most obvious one that as this large ice sheet shrinks, water is moving into the global ocean. And so that's what causes our global average rise in sea level. But there's also two slightly more complex processes going on. So this large ice sheet on the left here was previously exerting a gravitational attraction on the open ocean, pulling water towards the ice sheet, and that results in elevated sea surface height close by the ice sheet. Whereas when that ice sheet is melted, we have a reduced gravitational attraction, and therefore water is flowing away from the ice sheet, and we actually see a sea level fall or a sea surface height fall nearby the ice sheet. And as well as this, we also have crustal deformation. So this large load on the crust is reducing in mass, and therefore the crust beneath it begins to rebound. And we have this upwards and outwards motion in crustal deformation beneath where the ice sheet is or was. Okay, and so both of these kind of processes combined actually act to reduce sea level close by that ice sheet as it is melting, which is somewhat counterintuitive. Okay, so these processes create a spatially variable pattern of sea level change across the globe, and on elastic timescales, we call these sea level fingerprints. So that's what I'm showing you here, the sea level fingerprint of melt for Antarctica and the Greenland ice sheet. And so what these figures show is if we were to melt enough ice from Antarctica, for example, to raise global average sea level by 1 meter, this is the spatial distribution of sea level change that we would actually see due to those two processes. And the same for melting of the Greenland ice sheet here at the bottom. And so we're starting to see here that depending on where we are on the globe, we're going to see a very different response to the melting of these ice sheets. And so these sea level fingerprints can be broken into two different parts, as I've kind of alluded to here. There are a combination of changes in the sea surface, which is defined by gravitational equipotential, which we refer to as G. And the other component is the deformation in the sea bottom, so the change in height of that crust, which we refer to as R. And so when we calculate sea level change, we actually calculate these two distinct fields. So the one at the top here, this is an example for the Greenland ice sheet. The field at the top here is showing those gravitational changes in the sea surface equipotential. And the field at the bottom here is showing the solid earth deformation. And so these two fields that we can calculate actually depend on one another. So we need to know where the ocean loads will go to figure out how the solid earth is going to deform. But we also need to know how the solid earth is going to deform to figure out where the ocean will flow to. And so this is sort of a coupled iterative calculation that we solve. But each of these fields individually has important implications for sort of earth science problems and society. And so today I wanted to focus on each of these fields individually and talk you through a bit what's more details of what's going on here. So we can already, by taking a look at these maps, we can already start to answer that first question that I posed. We can take a look at our sea level fingerprint for the Greenland ice sheet and say, okay, well, if the Greenland ice sheet melted enough to raise global average sea level by 1 meter, if we're in California on the west coast of the US, the sea level rise that we would actually see would be lower than global average. It would be around 0.67 meters because of those two combined effects. Whereas if we're in Berkeley and the Antarctic ice sheet starts to melt, we're actually in much more trouble because the sea level rise that we're going to see is going to be larger than average because of those two combined effects. So these spatial patterns of sea level change are going to really matter moving into our future in terms of coastal change. So as I've alluded to, as well as these short timescale processes, the Earth is also responding to changes in ice sheets on much longer timescales. So the amount of ice on Earth's surface has changed dramatically through Earth history. And this plot that I'm showing on the top right here is an oxygen isotope curve, which can be used as a proxy for ice volume on Earth's surface. And so these kind of lows in blue are glacial maxima, and the highs in red are glacial minima. And so at the last glacial maximum, around 21,000 years ago, we had these large ice sheets present across much of the northern hemisphere. So that's what I'm showing on the bottom left here. We had large ice sheets across North America, Europe and Asia and Greenland, and those ice sheets gradually retreated to their present day positions. But the Earth is still rebounding from that loss in mass over the last 21,000 years at present day. And so because this is a longer timescale process, the Earth is acting more like a viscous fluid. So beneath where that ice sheet was, the mantle had flowed out to what we call peripheral bulges. And now that that ice sheet, that large load on the crust has been removed, that mantle material is flowing from these peripheral bulges back beneath the ice sheet and causing that uplift beneath where the ice sheet was. And the other thing to note about this is as that solid Earth material is flowing to different places on the Earth's surface, that also is going to change the gravitational field. So this is also something that we see perturbing that gravitational equipotential that defines sea surface height. So the first article to capture all this mathematically was published in 1976. And this paper by Farrell and Clark in 1976 developed what we now refer to as the sea level equation. And this sea level equation and this figure that they came up with here on the left actually captured a lot of what I've just described to you. So this kind of theory is really stood the test of time. And we now use this sea level equation in our sea level models, but we have updated it a little bit. So we now account for shoreline migration, which is the on-lap or off-lap of water on coastlines as sea level rises and falls. And we also account for perturbation in Earth's rotation axis. And so this sea level is purely water flowing where gravity and deformation tell it to. It doesn't include any thermal expansion of the ocean or ocean dynamics. And so the two inputs that we generally would need to run this kind of sea level equation model is an ice sheet history. So an idea of how the ice sheets have changed through time, and also an Earth structure model. So for short time scale problems, we usually focus on an elastic Earth structure. Okay, so then for the rest of the talk, I want to focus on mass loss of the Greenland ice sheet over the last 2 to 3 decades. And as I mentioned, I'm going to split it into first thinking about those changes in sea surface height. And then later on in the talk, we'll come back to the patterns of crustal deformation that are also occurring due to these changes in ice mass. So this first kind of project here on sea level change and sea surface height change was done with a lot of great collaborators, some in connection with Harvard University, and particular Songdangadrop at Tulane was a great help in terms of analysing satellite data and understanding sea surface height measurements. So, as I told you then, since the 1970s, the sea level modelling community has been developing these models to predict change in the sea surface height as ice sheets melt. And what I wanted to ask them is, can we actually validate those models of sea surface height change with observations of sea surface height over the last 2 decades? And while this may sound relatively sort of a basic step, this is something that hasn't really been accomplished well in the past. So previously, people have looked at ocean bottom pressure measurements, satellite altimetry data and tide gauges to try and see this pattern, this fingerprint of sea level change in observations. But there's really been limited success, and people have struggled with low signal to noise ratios, meaning that really only a small portion of these kind of data sets has been able to be explained with these sea level fingerprint models. But previously, people have focused on the far field areas from the ice sheet. So in the equatorial region, for example, where we have more data, we have a lot more ocean bottom pressure measurements, for example, but we have very small gradients in sea level change because of these processes. And so it really makes sense to look in the polar regions around these ice sheets where we're going to have the largest gradients in sea level change to detect. Okay, so what do we need in order to do this kind of model validation exercise? We need an observation of how sea surface height has changed over the last couple of decades, and we also need a model prediction of how sea surface height has changed over that same time period. So let's start with the observations. For our observational data set, we use satellite altimetry data. So there's a whole range of satellite missions that have been orbiting Earth, taking repeat measurements of sea surface height relative to their positions, so that we can track how sea surface has changed through time. And we now, because of all these different satellite missions, we have around 30 years continuous sea surface height data. And importantly, developments in these satellites over the last couple of years have meant that we now have higher resolution data at high latitudes in the polar regions. So we can now see a large area around the Greenland ice sheet where we didn't previously have measurements before. So on the left here, I'm showing the kind of data sets we can get from these satellite altimetry measurements. So here I'm showing you average change in sea surface height, averaged from 2002 to 2019 in millimeters per year. So here the areas in red are where sea surface height is falling, and areas in blue are where sea surface height is rising. And so we know within this data set that we're seeing, or we hope we have, the geophysical fingerprint of sea level change from melting of the Greenland ice sheet. But there are also a number of other signals that are going into the satellite altimetry data and changing sea surface height. So the kind of first additional signal that we have is we have meltwater from other global sources. So for example, melting of mountain glaciers and melting of the Antarctic ice sheet will also be affecting Greenland, sea level around Greenland. And we also have a signal from thermal expansion. So as the ocean warms, that volumetric expansion of the ocean will also be acting to potentially elevate sea surface height. And so for the purposes of this study, initially we don't assume that these two sources are probably relatively spatially uniform around Greenland, and so are likely to introduce sort of a shift in our measurements, but not any spatial pattern. And so we begin by neglecting those. But there are two things that we do need to worry a little bit more about. So within the signal, there's likely to be a perturbation to sea surface height caused by ongoing deformation associated with the decay of those large ice sheets since the last glacial maximum. And there's also likely to be an ocean dynamic signal, so an effect of large-scale ocean circulation perturbing sea surface height around Greenland. There we go. So first, let's take a look at that ongoing deformation from last glacial maximum. So in order to get an estimate of what this contribution to sea surface height change might be, we run a viscoelastic sea level calculation from 21,000 years ago to present day, and we take a look at the ongoing changes in sea surface height due to these processes. And so what we actually see is that the rate of deformation occurring is relatively slow, and therefore the gravitational changes in the sea surface height are also relatively small and relatively uniform. And so, this is pretty great that I'm showing you a very flat, empty plot here, because it means that we can probably neglect this process and kind of move on with our analysis. Okay. So then let's take a look at ocean dynamics and try and perform an analysis to remove that ocean dynamic signal that we're not interested in this data set. So as I mentioned, what I mean here is the variation in surface currents and large-scale ocean circulation that's causing warping of sea surface height. And so that's particularly apparent in the subpolar gyre region here, to the southeast of Greenland. And previously, these sea surface height changes have been connected to large-scale ocean circulation that's thought to be largely wind-driven. So what we can do here is, take a look at how well these changes in sea surface height correspond with wind patterns, and see if we can use that to remove this unwanted signal from our data set. So what we do then is we take a wind stress, take a field of wind stress predictions, specifically wind stress curl, from an atmospheric reanalysis model. And we do a maximum covariance analysis to find the principal components that are correlated between these two fields. Sorry. Oh, wow.
Would that be over the same time scale of the...
Yeah. So the full data set goes across 30 years or 27 years. And so actually averaging out that full time period removes some of this signal. And so we use kind of that full time period to use all the data that we can, but then we can also apply that sort of correction that we get from the full time period to shorter time periods too, because it is applicable over the shorter time period. So what I'm showing here then is the first four principal components that are correlated between these two fields, sea surface height and the wind stress curl. And we use these principal components then to get an estimate of the ocean dynamic variability in the original field. And so that's what I'm showing you here on the right, the signal that is thought to be explained by the wind stress curl, that can we therefore remove from this observational field. Okay, so then this panel on the right here is those observations corrected for this covariance with wind stress curl field. And what we're starting to see then is we've removed a lot of that variability that's around the subpolar gyre. And we're also starting to see this sort of concentric pattern where we have a little bit of sea level fall close to the Greenland ice sheet, and then we have progressively larger sea level rise moving away from the ice sheet, which is indicative of that kind of fingerprint pattern. And so the regression explains 90% of that local SSH variability around the subpolar gyre region. So we're kind of removing that trend well. Okay, and then as I mentioned, the second thing that we need is a model prediction over that same time period of sea surface height change. And so what we do then is we use up-to-date high-resolution estimates of mass change for the Greenland ice sheet, and we include surrounding glaciers too. So we also have mass change in Iceland, Northern Canada, Baffin Island. And we put those ice mass balances for the Greenland ice sheet into our sea level model using an elastic Earth structure. And we come up with fields for sea surface height over the same time period. So that's the figure that I'm showing you on the far right here. Again, this is a rate of sea surface height change in millimeters per year. And so if we take a look at the areas around Greenland, we have that concentric pattern of sea level fall close by Greenland and progressively larger sea level rise further away. And if we start to compare our corrected sea surface height measurements from the altimetry and our model observations, we're starting to see these things are looking relatively similar, which is exciting, in my opinion. And so then the final thing that we wanted to do here was say, okay, how similar really are these two fields to one another? Is this statistically significant that we're detecting this fingerprint signal? And so we did a couple of tests. The first thing we did was we plotted a profile along the west side of Greenland here. So in this figure here, the observations are on the top here and the predictions are this shaded line below. And what we start to see is the gradients of these two lines along the profile are relatively similar. So that's convincing. We do have an offset between our predictions and our observations, but actually that's what we expected because, as I mentioned, we're not accounting for sea level change due to mass loss from Antarctica, for example, and thermal expansion. So it's kind of a good thing that our observations are slightly higher in rate than our predictions. Okay. And then we did some statistical tests. So here I'm plotting observed sea surface height rate and predicted sea surface height rate everywhere within this red box here on the map. And those points are sampled relative to the resolution of the data set because resolution reduces as you move further north. So it accounts for those resolution changes. And we calculated a slope and a Pearson correlation coefficient. And what these things indicate is that there is a significant linear association between these two fields. And the slope indicates that the offset between the observation and the prediction is relatively consistent across the region.
What's the significance of the shape of the box? Like with a little corner and not just being the whole area?
Yeah, so we kind of chose this box before we knew how well we were going to be able to remove the subpolar gyre region. So the idea is that this would include, less of the ocean dynamic signal that would be affecting our, the sea surface height measurements, and also would be including less of what's going on with Iceland. But yeah, it is a bit of a weird shape to choose. I get that. It was one of those towing the lines between we didn't want to exclude all the data that made our correlation less good, but there was also physical reason to be excluding some of it.
So can I ask a question? Just on the slide before.
This one, or?
This one, yeah.
Yeah.
I guess the red on land, does that indicate uplift?
So if you were looking at a pattern of sea level change, total sea level change, it would, but this is just the sea surface height. So this is just the change in gravitational equipotential, which isn't really a physical quantity on land.
I see, yeah. I see, right.
Yeah.
So this is sea surface height because you've just got altimetry measurements.
Yeah, exactly, yeah.
Okay.
Yeah, so these statistical tests really show that there's a statistically significant correlation between these two fields, actually with a p-value of less than 1%. So we're showing a robust detection of the fingerprint of sea level change from the melting of the Greenland ice sheet. So the kind of implications of this then, this study gives us a robust map of the impact of ice mass flux on the global ocean and the ocean surrounding Greenland. And it also demonstrates that these fingerprint type geometries are rapidly established in our oceans. So these fingerprint patterns are occurring on the scales of years to decades, rather than taking a longer time period to be appearing. And so understanding these patterns allows us maybe from future data sets to tease apart the different melt sources, different ice mass centers that might be contributing to sea surface height changes in different data sets. And importantly for the modeling community, this work validates decades of theoretical and numerical developments in the sea level modeling community on these sea level fingerprint models. So in future, these methods of analysing and utilising altimetry data to observe these large-scale geophysical patterns of sea level change can be applied to other areas. So the obvious kind of next step is to say, okay, well, we've seen this around Greenland. Can we also detect a fingerprint signal around Antarctica? So Sonka and I have an undergraduate at Old Dominion University in Virginia focusing on this at the moment. There are definitely some complications with sea surface height observations around Antarctica, but I'm excited to see where this is going to go to next. Yeah, and I guess I'm kind of halfway through, so if there's any questions about this part of the talk, I'm happy to take them now, or I can, yeah, go ahead.
Well, there's some studies that say the viscosity on the Greenland is like an order of magnitude lower. In which direction would it change your answer, if at all?
Yeah, so I guess if the viscosity is lower, the uplift would be faster, and so the gravitational changes would be smaller because you would be replacing ice sheet with Earth, right?
Right.
Yeah, so it would probably reduce the gravitational effect in sea surface height.
Got it. Cool.
That absolutely fantastic p-value, is that mostly from the similarity of the slopes that you said were offset?
Yeah, so we specifically just correlated the rates with one another.
Okay.
So yeah, the kind of the slope value is showing you that there's a constant offset between the two, and the Pearson correlation coefficient. So yeah, referring to that gradient. Yeah.
Thank you very much.
Yeah. Yeah.
Is there a way to quantify the ocean thermal expansion, for example, to make sure that it really is the cause of the mismatch between the two?
Yeah, that's a really great question that I've certainly been thinking about how to do better, because it's not very satisfying to say there's a jump that could be ocean expansion. And I think there are some data sets now that would, kind of observations of stark changes in sea surface height that maybe would give us a better understanding of that. And I'm kind of working with some more ocean dynamic focused people at Los Alamos to try to quantify that, but I don't have a good answer for you yet. But it does seem, looking at some of those data sets that are available to us, that it may not actually be perfectly constant over the region. So that might be another signal that, could be introducing on a smaller, like a smaller magnitude of variation, but it might be something else that's contributing to the variability of the signal. Okay, shall I keep going? All right, so heading back to that crustal deformation side of things. So this work again was done in collaboration with a variety of people while I was still at Harvard. Some folks at Lamont, Jim Davis in particular, helping us with some connections to GPS data, and Matt Hoffman at Los Alamos. I've kind of continued this work in my postdoc too. Okay, so it's easy to justify why we care about total sea level, but why do we care specifically about what the crust is doing in response to these ice mass changes? Well, we have networks of GPS stations and tide gauges worldwide. And we use the 3D motions from those sensors to answer questions about earthquake and volcanic activity, about large-scale tectonics, and about glacial isostatic adjustment. And so in order to understand and disentangle those processes from one another, we really need to understand all of the factors going into that 3D motion signal. And that includes a signal for modern melting. So the idea of understanding 3D deformation caused by ice mass loss isn't a new one. People have been, modeling and observing changes due to that longer time scale, glacial isostatic adjustment due to ice mass loss from the last glacial maximum for several decades. So in the early 90s, people developed models for what they thought this deformation looked like beneath Scandinavia and North America as those large ice sheets. The present day motion from those large ice sheets that have decayed. And then in the early 2000s, people specifically set out to create observational data sets that might show this. So the Bifrost experiment across Scandinavia was one of these first examples where they put out this big GPS campaign to try and observe the signal. And what I'm showing you in the center here is the vertical motion from that GPS network. And then on the right-hand side, I'm showing the horizontal motion of those GPS stations. And so what you see here is that there is a clear uplift signal beneath where the center of the Scandinavian ice sheet was, and this outward spoke-like pattern in the horizontal motions away from that ice center. And so then more recently, people have tried to understand the 3D deformation generated by modern ice mass loss. And so here I'm showing a couple of those studies. So on the left, this is modeled uplift thought to be happening beneath Greenland over the last couple of decades. And then on the right, I'm showing you modeled uplift beneath Alaska as our Alaskan glaciers have lost mass again over the last couple of decades. And here again, you're seeing that really kind of stereotypical outward spoke-like pattern in the horizontal motions away from those centers of ice mass loss. But what all of these studies have in common is that they're looking in the region directly around the ice sheet or glacier beneath where that mass is being lost. And so what I wanted to do is extend these type of studies to say what's actually happening in regions far from the ice sheets and glaciers. Is that deformation widespread to regions far from these ice centers? And so 2 studies have come out in the last couple of years that have started to look at the more global nature of these processes. So this figure on the left is from Raver et al. That came out in 2017. And this is showing the vertical deformation due to ice mass loss from both polar ice sheets and from a database of mountain glaciers from 2003 to 2014. And the figure on the right is vertical deformation due to mass loss specifically from Arctic glaciers. And what you start to see from these 2 figures is that although the largest magnitudes of uplift are beneath where the ice is melting, the vertical deformation extends actually across large parts of the Northern Hemisphere. And so building on this previous work, we wanted to figure out what does the 3D pattern look like? Are there significant horizontal motions as well as these vertical ones? And we know that mass loss from ice sheets and glaciers varies dramatically year to year. So how are these deformation rates also changing through time? So just a quick overview of the methodology. We begin with a high resolution data set for the mass balance of our ice sheet or glacier. So a mass balance for Greenland in this case. And then we put those that observational data set into our sea level model. And what this gives us then is the gravitationally self-consistent redistribution of ocean loads and ice loads across the surface of the Earth. And then once we have those new ocean and ice loads, we use love number theory to predict the vertical and horizontal deformation caused by the movement of these loads at every point on the Earth's surface. And so this is the kind of output that we get. The color scale is not great on this, but I hope you can kind of figure out what's going on. So the vertical motion is shown in this color bar with areas of red being those uplifting and areas of blue, which you can sort of out across the middle here, areas that are subsiding. And then those horizontal motions are shown as arrow vectors. And what you can see is that around the Greenland ice sheet, it's very similar to some of those previous studies. So we have large amounts of uplift in areas where we're losing a lot of mass. But if we take a look at areas a little further away from Greenland, we see that both the vertical and horizontal deformation is extending large distances from the ice sheet. So we have vertical and horizontal motion on the order of up to 0.4 millimeters per year across parts of Northern Europe and Northern Canada and Northern US too, across this time period. And so that's kind of the average across the full time period, but what does that look like through time? Well, video works, we'll see. Oh, great. So here I'm showing you each of those year time slices. On the left, the deformation maps in the same color scale as I mentioned before. And on the right, the magnitude of those horizontal deformation vectors at specific sites. So the purple and orange sites on the map correspond with the purple and orange sites moving through time. And so what we're seeing here is that these horizontal motions are highly variable through time, and they do largely scale with the mass loss from the ice sheet. So in years where the Greenland ice sheet is losing more mass, we have larger horizontal motion vectors. And so then to just pause on that last time slice, we can see that in years of maximum melting of the Greenland ice sheet, we have horizontal motions on the order of 0.2 to 0.3 millimeters per year predicted across large parts of Canada and northern US and Europe. And we can also see that there's a large north-south gradient in both horizontal and vertical motions across large parts of these continents. And so then just to kind of summarize this and bring the other ice sheets into the picture too, we also did the same kind of model prediction for the Antarctic ice sheet and for a global database of mountain glaciers. And so here I'm showing you that in the different colors. So the blue lines in these figures are the deformation due to melting of Antarctica, green is the melting of Greenland, red is the deformation due to melting of that global database of glaciers, and then the total deformation is black. And that's at each of these 5 individual sites that are shown on the map on the left. And then just to orient you through the panels, this top row here is showing the vertical deformation without being positive. The middle panel is showing southwards deformation, horizontal deformation, and the bottom row is showing eastward horizontal deformation. And so what I want to point your eye to in this slightly chaotic figure is a few things. So I haven't talked that much about Antarctica, and from a deformation perspective, that's partially because during this time period, the net mass loss of ice from Antarctica was significantly lower than from Greenland or from mountain glaciers. And actually the distribution of ice loss from Antarctica meant that while one side of Antarctica was growing, the other side was losing mass. And so this deformation signal is relatively muted from the mass loss from Antarctica. And so even at sites proximal to Antarctica, like the Falklands, for example, the contribution that we see from other systems like Greenland, for example, is actually larger than we're seeing from Antarctica. Okay. And then to just bring your eye to this specific site at Norilsk in northern Russia, here this kind of reinforces the idea that the closer we are to the large ice sheets and glaciers, the larger signal that we're seeing. So in this site, we're seeing strong deformation due to those Arctic glaciers and due to Greenland in terms of sort of uplift as those glaciers lose mass and motion away from the Arctic in the horizontal. And then if we kind of take a look across all of these sites in the Northern Hemisphere, what we see is that even though these sites are relatively far afield from the Greenland ice sheet, all of them are really dominated by that signal of deformation due to mass loss from the Greenland ice sheet. So it's extending a long distance from the area that's actually losing mass. And so then to summarize, this study predicts that there are significant horizontal and vertical motions from modern ice mass loss that extend across large parts of the Northern Hemisphere. And specifically, this is a previously unmodeled process that likely introduces a temporally variable, systematic, and detectable signal in observational data. And what I mean by that is that maybe this is affecting our GPS datasets that we use for other earth science problems. So an important factor to consider here is that the variation in deformation that we see from these processes is larger than the error in GPS datasets that we're using for other things. So if we come back to this Bifrost experiment here, we see that the uncertainty associated with this dataset that was published in the early 2000s is smaller than the variation caused across the same region because of these processes. So by fitting this data without accounting for this modern melting process, we're likely introducing a bias into the results that we have from modeling studies that fit these surface observables. And so I guess kind of a natural next step then is to take a look at the GPS data set and say, okay, seen this in our model predictions. Are we actually seeing it through time in our GPS data sets in Scandinavia and in the US? And that's something that one of my colleagues, Evelyn Powell, and I are working on with Jim Davis at Lamont. But I also wanted to just talk a little bit more about where I'm going with this through my postdoc. So I've kind of shown you throughout the last few slides that we have deformation across the Arctic that's significant, particularly associated with Greenland and the Arctic glaciers in the modern. And we also have, in the same region, ongoing deformation due to the decay of those ice sheets from the last ice age. So there's a lot of kind of loading signals here that are going to be causing significant deformation in the crust and upper mantle across the Arctic. And so I'm starting to think about then, what effect is this deformation having on regional stress fields? So we know that low magnitude earthquakes and slow volcanic activity can be affected by small stress changes. So I want to ask, are these kind of stress and strain changes significant enough to be affecting hazards in the Arctic? And so from these kind of glacial isostatic adjustment models, we're able to directly calculate strain perturbations to the crust across the Arctic regions. So here's just an example. I'm showing dilatation, which is a measure of expansion and contraction of the crust. So green areas are areas where the crust is expanding, largely beneath where the ice sheets are losing mass in the modern panel here. And then the purple areas are the areas that are contracting. And so if we compare these two panels, so the panel on the left is the kind of recent deformation due to mass loss of these glacier systems in Greenland over the last 3 decades. And this panel on the right is the ongoing signal from the last ice age. And what we see, notice the different color bars here, is that the modern deformation that's occurring is as large or larger than the deformation that's occurring associated with the last ice age. And there have been several studies that have suggested in places like Scandinavia and Canada that we may have some small magnitude earthquake activity associated with deformation from these processes. So this is kind of making me think that, okay, these shorter time scale processes might also be having similar effects.
Can I ask one question?
Yeah,
So
yeah.
stress will be at the surface, or can you calculate in specific depths? Because earthquakes happen to some depths.
Yeah.
I
Yeah, right.
was wondering if you incorporate something to make sure the area events happen, how much stress happens.
Yeah, that's a really great point. So the kind of natural setup of our sea level models is just to look at the surface because sea level change happens on the surface.
Right.
But these models can be extended to apply this throughout the crust. So that I've kind of worked using that love number formulation to also calculate the deformation at any point within the Earth, and then use that, yes, to calculate strain and stress changes within the Earth too.
Thank you.
Yeah. What else is here? Yeah, so kind of the next step for me, which I'm also interested to talk to you all about, and I already touched on a little bit with Roland, is there a way to use some kind of event-based probabilistic seismic hazard analysis to look for a correlation between perturbations to the strain field and the type of earthquake activity that we might be seeing? And I'll just finish up by saying that I think this might be a relatively hard problem with historic data, but it also has implications for the future. So unfortunately, mass loss in the Arctic is accelerating. And here in the right-hand panel, I'm showing you a couple of predictions of what might happen by 2300. And so we can see that, you know, the ice mass loss is sadly going to accelerate, and therefore our stress and strain changes are also probably going to be larger in the future. But we can apply this same framework to calculate the changes in stress due to these kind of future processes, and maybe get a bit more of a handle on how this might be affecting earthquakes and other hazards in our future. Yeah, and also just end by coming back to learn my little diagram of sea level change one more time and saying I hope that I've showed you today that accurately capturing geophysical processes does further our understanding of regional and global climate systems. And it's really necessary to understand the full picture of climate change and the potential hazards that we might be facing in our future. Yeah, I'm happy to take any more questions.
No, I just have more of a comment just to relay the point that you made about the modern changes.
Yeah.
And I think you touched on it earlier, but you know, you're looking at the strains, but also the strain rates, right? When you have sudden changes, and you know, these ice sheets are collapsing at really non-linear rates. So yeah, at times it could be extremely I mean, the strain rate could be quite high, right? Elevated when you have sudden collapses of ice shelves or whatever.
Yeah, I think so.
So looking at the rates would be kind of interesting too.
Yeah, and I think while people have started to do this kind of work around Greenland, it doesn't seem, and in Alaska, there's been quite a lot of work in Alaska too, but it seems like a lot of the rest of the Arctic hasn't necessarily been considered because, you know, the melting's only really been getting worse over the last couple of decades.
So as you was saying, right, this effect is pretty small, but it's near global. But I wonder, you were saying that could bias, you know, studies of other processes. But do you think people that are developing the International Terrestrial Reference Frame System, right, they would worry about that? And I mean, Yunchim Davis may have talked about that because that's something that he would care about.
I think it is something that should be worried about, but at present isn't being, because the kind of corrections that reference frame would account for would be like more global in scale, whereas while these processes are long wavelength, they do have like a specific regional pattern that probably isn't captured in anything that's already done in that.
Because they try to tie themselves right to a plate tectonic framework, neutral one, and this would change the rotation parameters.
Yeah, and my sense is that it's not being accounted for at present.
Yeah. Cool.
Yeah, I guess I could just use a little more help from a sort of process perspective. Like on the sort of the long wavelength signature of the glacial isostatic, I guess one of these longer timescales makes sense as you sort of illustrated, connecting it to sort of large scale mantle flow. I guess I'm having a harder time with that with this short term elastic response because it looks like this very smooth signal. But like as you're coming off from Greenland to mainland Canada, you're like going where like oceanic lithosphere is being produced. You're plotting all these plate boundaries and just isn't that going to factor into the elastic response, or am I missing something?
No, you've hit on a great flaw of these models actually. So a lot of these models assume a 1D Earth structure. And so that was kind of like the initial situation that we're working with, that the Earth is radially symmetric and none of those complexities in the crustal structure and the plate boundaries, for example, are captured. But within our group, Konstantin Matichev, who Harriet and I have both worked with, has developed a 3D model to do the same kind of things. And so that includes a more complicated elastic crustal structure. And that is also kind of one of our next steps to say, okay, well, does this actually really hold when you're on the other side of the mid-ocean ridge, for example, or is some of that motion not being propagated in the crust?
Yeah, because I guess that would be my intuition that would really significantly attenuate the effect and make it be a much more local rather than, I mean, you were sort of showing like that there's a signal in India, right? Like so we're crossing like multiple.
Yeah, and so I guess it comes with a caveat that it's probably mostly accurate across like the continent, like Europe, for example, but then maybe when you're on the other side of the Atlantic, it's not. And so that's also why I think this next step of actually looking at the GPS data and saying, can we identify this in Europe and in North America is really important too. Because I feel, tentative going to the GPS community saying account for this when we haven't seen it ourselves.
I think those effects would be stronger in the kind of viscous timescales,
yeah,
right? Because on elastic Earth, actually the variations laterally are like 1% variations, and maybe it would be less on these kind of modern timescales. The variation.
Yeah, I think that's
structure. If you look at a mid-ocean ridge at an elastic timescale and a crater on an elastic timescale, the similarities closer than if you look at a mid-ocean ridge at viscous timescale and a craton at a viscous timescale, if that makes sense.
But if you're visiting this very much on elastic temperatures, you're showing
Right.
year to year.
Yeah. Yeah.
They
And I
look
think-
more similar.
Yeah, I think Constantine's initial work shows that like on the year timescales, like it is reasonable to use a more 1D elastic model even across that, across the plate boundary. But yeah, it's something we're working on fully figuring out.
But if it's like 0.4 millimeters, 0.1 millimeters, probably is gonna like
Yeah,
work into that, isn't it? Yeah.
yeah.
Are there some low magnitude earthquakes that have been identified that are potential candidates where you are predicting more horizontal deformation or maybe some structures could be getting reactivated? But
Yeah, so I won't say I've got as far as identifying particular events, and I'm not quite sure, how the progression is going to go. But certainly there are in places like Svalbard, just away from the ocean ridge, there's quite a few earthquakes, and Los Alamos in particular are very concerned about any earthquakes that might be happening in the Russian Arctic. That's where they have these test sites, but it's also where they have a lot of data that your average Joe might not be able to access.
Are you allowed to say this stuff?
Yeah, you're allowed to know what they've got, just not like what it is. Yeah, so I don't know, watch the space.
Or not?
Oh, yeah. I'll see if I can tell you.
Can I ask a question?
Yeah.
In the uplift map related to Greenland melting, specifically the vertical one, you had like a lot of red, but then in north, I think it was like northeast of Greenland, there was subsidence.
Right here.
Yeah. Yeah. Can you spell that?
Over this time period, in an average sense, there's actually ice mass growing there.
Oh, really?
Yeah, but I think that, that's because it's averaged over a long time period. You wouldn't in each of those years see ice mass
So
growing.
that's higher snowfall?
Okay.
Any more questions? Yes.
Maybe something not related. How big the effect has to be in order to affect the moment of inertia of our planet, such that we have to consider to change the length of the day?
The length of the day.
Or something, or some modification. Can it be at all? Should we consider? From time to time, people talk about the inaccuracy of.
Yeah, that's an interesting
So
question.
you change them. You dislocate the mass in some sense.
Yeah.
The moment of inertia is changing, tiny. Over many years, I don't know. Never thought about it.
Yeah. Yeah, I mean, there's certainly a true polar wander signal associated with these changes, but in terms of like actually changing the rate of rotation, I'm not sure. It's something that I haven't thought about a lot, but
I think these changes change the direction of the angular momentum vector, but I don't know if they change the length that much, which would be.
I mean, there are some invariants, but there's I times omega, if I remember from high school.
yeah. Yeah. I don't know. I'm not quite sure. I would guess that these
It would be a small effect.
Tiny,
Uh,
tiny.
Yeah.
So,
but maybe measurable.
that we changed from the.
Big earthquakes have been
Yeah.
calculated, for the Sumatra earthquake, where the change in length, and it even made headlines. And,
Yeah.
in terms of mass transport, that's probably comparable, just somewhat different.
Once we changed from the Julian to the Gregorian calendar.
All right, thank you so much.
Roland, are refreshments on the balcony?
yes.
Has the weather gotten better?